Until now, we only consider algorithms that try to solve critical section problem in between two processes. You probably ask how to solve the problem when you have more than two processes. So the Baker algorithm is a mutual exclusion algorithm designed to solve the critical section problem for multiple processes. It guarantees that only one process can execute its critical section at a time while satisfying mutual exclusion, progress, and bounded waiting. In this algorithm, each progress is assigned a number similar to taking a ticket at a bakery. So the algorithm works as follows. Upon entering, a process takes a number that is greater than any number it has seen so far. The process then goes through a series of rounds where it compares its numbers to the numbers of the other processes. So the process with the lowest number gets priority. Okay. So if two processes have the same number, the one with the lower process ID gets priority. Once a process has obtains the lowest number, uh, lowest number, and all of the other processes with lower numbers have finished their critical sections, it can enter its critical section. After executing the critical section, the process releases its number, it makes it 0, and allows other processes to take their turn. So the bakery algorithm guarantees mutual exclusion because only the process with the lowest number gets to enter the critical section. It also satisfies progress because if a process has a higher number, it will eventually get a chance to enter the critical section as long as all processes eventually finish executing their critical sections. Additionally, it ensures bounded waiting since each process is assigned a unique number and the process with the lowest number gets priority. Overall, the bakery algorithm provides a solution to the critical section problem for multiple processes, okay, by assigning numbers and determining access based on those numbers, which guarantees mutual exclusion, progress, and bounded waiting, which are requirements for a good solution to a critical section problem. So a valid solution to the critical section problem can provide robustness against process failures in the reminder section, but not in the critical section. Failures in the reminder section are handled because they are equivalent to having an infinitely long reminder section. However, a process failing in its critical section cannot be detected or signaled to another process, leading to potential deadlocks or violations of mutual exclusion. Additional mechanisms are needed to handle failures in the critical section, such as maybe timeouts or process monitoring. So let's look at software solution for addressing the critical section problem of its drawbacks. Okay. So first one is delicacy. So software solutions heavily rely on correct implementation and proper synchronization mechanisms. Small errors or oversights in the code can result to issues such as race conditions, deadlocks, or live locks. Ensuring the correctness of software solutions can be challenging, and even minor bugs can have significant consequences. The other one is busy waiting. In many software solutions, processes that are requesting to enter their critical sections often use busy waiting, where they repeatedly check for the availability of the critical section. This consumes processor time needlessly, as the process keeps executing instructions in a loop without actually making progress. Busy waiting can result in inefficient resource usage, or maybe lower system performance and increased power consumption. Yeah, we can say that. So if critical sections are long and process is waiting to enter, it would be more efficient to block or suspend that process. instead of letting it continuously check for availability. Busy waiting in such cases can waste CPU cycles and delay other processes that could utilize the CPU more productively. Blocking processes until the critical section becomes available can improve overall system efficiency. While software solutions provide flexibility and they can be implemented without relying on specific hardware features, these drawbacks can impact their performance and efficiency. Hardware-based solutions or a combination of hardware and software approaches are often employed to mitigate these limitations, which we will see next week.